two binomial distribution. That's why we put them together. Okay, and but instead of like have the trail like n trail of binomial experiments, we define in terms of time. It could be time, it could be space. I'll be more precise later. But let's say that suppose we want to find probability distribution of a number of automobile accidents at an intersection in 1 week. So instead of trails, we have time here instead, 1 week. Okay. And obviously, the number of automobile accidents cannot be 1.5, right? It has to be an integer or number like 0, 1, 2, 3, 4. So it's still included in discrete random variable because the outcome cannot be decimal place, the decimal point, like cannot be 1.5, 2.75, things like that. They have to be whole number or integers. Okay, so if 1 week, however, is split it up into n subintervals, each of which is so small that most one accident could occur in it with non-zero probability. So let me explain more on this point, okay, and how it related to binomial distribution. Okay, so we say that it's time. Okay, so let me draw a timeline. Okay, so let's say that this is timeline. Okay, in 1 week. And suppose that so I put a red dot for accident, right? So it could be start from 0 here, right? When we start counting and we found like this. Okay, so we found like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We found like there is 10 accidents. Okay, 10 accidents. So now within this time, what we can do is we can split it, right? So that the whole time period that we observe is this length, but then we split it. Okay, let me use another color like this. Okay, and suppose that you can see that the way I split, right? In each, what we call subinterval, in each subinterval, there are either one accident or no, right? The way I split, and I haven't counted the number of the subinterval yet, but let's call it n subinterval. But you can see that by splitting time into n subinterval, it becomes something like binomial experiments, whereas like the first subinterval, there's no accident, 0. Second, 0 again. The third, 1. Okay, accident happen. No, accident. So in each subinterval, it either have accident or no accident. So it like this is become n trail in binomial distribution. Okay, but I can increase n. Okay, so So I can even like, let me use a black color. I can like split each interval into two, right? But as long as I manage to still have one accident per sub-intervals, so I can increase the number of sub-interval into like n to be like 2n, 3n, or go to infinity. If n go to infinity, you're gonna have a smooth timeline without any sub-interval. So this is to say that, in a sense, Poisson, right? Poisson distribution is like take limit from n to infinity of, okay, just say binary. So this is not it's incorrect mathematic expression, but I want you to see that we will show the correct mathematic expressions, but this is like to see that Poisson distribution is a binomial distribution where the number of trail is go to infinity. So instead of have like 10,000 of trails, we imagine that it go up to infinity and it becomes smooth, one smooth space of time. Okay, so that is a connection between the two, and that's why we choose to study Poisson distribution here. Any question? Okay. So let's go back to the PowerPoint. So still within this, when we split the timeline to n sub-intervals, and we know that in each interval either one accident or no accident. So we can define like in binomial distribution that 1 minus p is probability of failure or no accidents, and p is probability of having an accident within the sub-interval. So binomial is, as I say, is the Poisson is a binomial distribution where the limit is go from n go to infinity. Okay. In the Poisson distribution, we're gonna have this lambda, right? And lambda gonna equal to n time p. N time p, if you remember in binomial, is expectation, right? If we go to binomial, in binomial, the number of trail n times the probability of success is the mean of binomial distribution. So in a sense, in Poisson, lambda represents the mean. But let me show you why we have lambda, because n will go to infinity, right? So if we have n, then we cannot replace n with infinity, but we can show that when n go to infinity, it become n times p become lambda. Okay, so this is okay. I'm not gonna explain all of this, right? But I'll show you how it works. We're gonna talk briefly, but basically, below here, this is the probability density function of binomial distribution, and we can show that we obtain this by taking the limit from n to infinity of the PDF of the binomial distributions, okay, which is this. So you can see that this is what we have seen before, PDF for the binomial distribution. We have C and Y, and we have p to the power of y, and then 1 minus p to the power of n minus y. So this is what we have seen. And this is something new. We take limit of n go to infinity because we say that Poisson is just binomial when n go to infinity. Okay. So you can see that now we have lambda, right? So because we have p, right, p here, but we just say that we're gonna use the new parameter. So lambda is n times p, so p is n divided, p is lambda divided by n according to this relationship. So what we do here is that we replacing p, right, this is supposed to be p, this p to the power y, to be lambda divided by n to the power y, right? And this again, this 1 minus p become 1 minus lambda over n. And this is still another is an expression for n, c, and y. But after you work through, right, this is the bit where we can take it out of the limit. Right? We move this in front of the limit because the limit only interact with n, right? So this term lambda to the power y divided y by y factorial, there is no n in it, so we can take that to be in front of limit, and the limit only apply to this term. But let's take this term here, 1 minus 1 over n. So if n go to infinity, right, if this become very big, so 1 divided by n is closing to 0, okay? So this become 1 minus 0 or just 1. So this trick work for many terms that involving n, that n is in the bottom, in the denominator, because when n go to infinity and you have n divided something, it will go to 0. The only term left will be these two terms, and especially this term. And so the limit of this term is actually epsilon, oh sorry, not epsilon, exponent base, right? Natural base, e base, to the power of minus lambda. So eventually we have lambda to the power y divided by y fact, and whatever in this limit, it just boils down to e to the power of minus lambda. It looks complicated, right? Yeah, but just to say that, okay, we started binomial, we take limit of n to infinity, and we got the PDF of a Poisson distribution. It looks scary because it have e, right? But I will show you in a minute that it's not that difficult, right? Even in iPhone, you have e, right? So okay. So in iPhone, right, calculator, so if you turn it this way, then you're gonna have e to the power of x like this. Okay. So if you want, I think minus 1 and e to the power of minus 1, just that. So it looks scary, but it's not, right? You have your calculator. You cannot use your mobile phone in the examination, but you can have calculator and you can calculate e to the power of any, like negative 1, right? Let's see, 1 and e, yeah. See, e to the power 1, so it's 2.718, right? And we know that, okay, this is a value of e to the power 1 or just e, but is this a correct value of e? Same as pi, right? Pi, remember, pi 3.1415, whatever. But is that, okay, let me put, we have a pi here. Yes, okay, I have a pi here and I have this number. Is that a real value of pi or an approximation? Approximation. Why? Because pi is a number that you have an ending decimal point, right? They have actually a competition where you compete to calculate the decimal point of pi, right? And you can win money doing that, right? I think that the record is, I don't know, maybe in the millions. Okay? But e and pi is the same thing. Is what we call a rational number. So it's a number that you cannot express in terms of ratio, right? Rational is adjective for the ratio. So we have to depend on the calculator to calculate e, but it's not that difficult. Okay. Anyway, let's see. Let's see like how we can work out the problem with Poisson distribution. Okay. Poisson is discrete probability distribution, and it refers to the number of events or successes within a specific time period. Or it doesn't have to be time, it could be a region of space. Yeah. For example, number of accidents in one day on a particular stretch of highway, so that is space of time. The number of floors in a, I think it could be cloth, the bowl cloth. Okay, so it's a piece of cloth basically, yeah, just a unit of cloth. So that the second example is when you refer to a space, not a time space, but the area, right, on the cloth. And it could be like the number of cars arriving at a service station in 1 hour. So again, we're talking about time space in 1 hour. Okay. The interval is defined by both time, right? It could be 1 day or like a space, like a particular stretch of highway. Like Benjamin experiment, a Poisson experiment has 4 defining characteristics. 1, the number of successes that occur in any interval is independent of the number of successes that occur in any other interval. So if we have 2 intersections, right, we assume that, or maybe like we can have 1 intersection, but we have 2 time periods. Let's say like we record the number of accidents in April and the next time in May. And we have to assume that the number of accidents in both April and May are independent from one another. Okay. So that is the rules number 1, which is close to the rule of binomial distributions. Second, the probability of success in an interval is the same for all equal size interval. Right? So we're talking about P, and P have to be the same. Like the probability of having accident will be the same within the month of April and the month of May. Right? We have to let's say like 1 month is 30 days, right? And then we assume that the probability is remain fixed. Third, the probability of success is proportional to the size of interval. This number 3, you will see that we're going to use it. So this means that if we talk about, like if example give you a 1 month, okay, and then it asks you to calculate the probability for 3 months. So 3 times the time space that is given. So the probability have to be increased 3 times as well. Because we have 3, instead of 1 month, we have 3 months. So the probability of having accident within 3 months will be 3 times of that in 1 month. So the probability of success have to be proportional to the size of interval. Number 4, the probability of more than one success in an interval is approach zero as the number of interval as the interval becomes smaller and the number of interval increasing to infinity. Right? We assume that each sub-interval either have one accident or no accident at all. Okay. Okay. So the Poisson random variable measuring the number of successes in that time space or in that area. Okay, so if we say that on average 96 trucks arriving at border crossing every hour. So every hour is the time space here, right? So it means that time space is 1 hour, and on average, it's implied this is mean, right? So 96 here is the mean of the Poisson distribution, which is lambda, right? Because lambda is equal to n times p, which is the mean in a binomial distribution, and Poisson is just extensions of binomial distribution, so it have to be 96 to be your lambda. Or it could be a number of typographic errors in a new textbook, right? On average, it's 1.5 per 100 pages. So we have in a space of 100 pages, on average, we have 1.5 typo, like mistakes, misprinting in that 100 pages. We will see an example that if we increase, right? If we increase from 100 to 400, the average will increase 4 times because the probability of success can increase 4 times as well. Okay, that is we've seen the density already, and y can be 0, 1, 2, 3, and so on and so forth, right? And lambda have to be non-zero, greater than 0. And the mean, right? Mean is the mean here, or expectation of y, where y is the number of success here, is lambda. So in some book, instead of using lambda, they're just using mu instead. So they just like, instead of having lambda here and lambda here, they just put mu instead of lambda because mu and lambda is the same thing. So it depends on people who wrote the textbook. And you can see the variance is also lambda. So Poisson distribution has this weird properties where the mean and the variance is the same. Okay, hopefully when you see example, it will become more understandable. Okay, now, first example, this, again, using the example textbook, okay? There some analysis conclude that the number of errors is Poisson distributed. So you can see here that is Poisson distribution because it's the question gives you the information with the mean of 1.5 per 100 pages. So in this example, the interval is in space of 100 pages and the lambda is 1.5. Now, the question is, the instructor randomly selected 100 pages of a new book. What is the probability that there are no typos? So it asks, what is the probability of y equal to 0? Okay? So you have to translate the question. So it asks, well, what is the p of y equal to 0? And we use the formula for the Poisson distribution, and then we replace with what we know. We know that lambda is 1.5, right? Y is 0, so we have that. So you can see that 1.5 to the power of 0 is 1.5 to the power of 0 is what number? 1. And 0 factorial is 0 factorial. It's not 0, right? 0 factorial is 1. So it means that that is 1, that is 1. So it means that this probability is just e to the power minus 1.5. Okay? So we do that, right? So we have 1.5 negative, 1.5 negative number. Is it? Okay, and then we press e to the power of x. So you can see that that number, right, that corresponding to the number you have on your lecture note. So 0.223130, so it's about 22% chance of happening. So as long as you can remember the formula, right? So e to the power minus lambda multiplied with lambda to the power y divided by y factorials. As long as you can remember that, as long as you know what is lambda, what is y in the equation, and you can calculate the answer easily. Okay, so the background is quite complicated, but the calculation is not. Okay, so now we can using R as well. Okay, so this is from last year already have this in the final exam. Okay, so we have similar to binomial, we have D Poisson, P Poisson, Q Poisson, and R Poisson. So usually we use D and Q, and D is a density function. You can see that D is when you want to find what is the probability of y equal to x. Okay, this number. P, right? P, you can see lower the tail equal to 2. So this is cumulative probability distribution, or CDF. So this is when you want to calculate like what is the probability of y less than or equal to 4, for example. Okay. We'll see more example of D and P. Okay. Let me ask you, if we were to use these two codes to answer the question that we just did, right? We want to calculate what is the probability of y equal to 0. Which one you're going to use? D Poisson or P Poisson? D or P? You want to know what is the probability of y equal to 0? Exactly 0. Not less than or more than. Which one? P or D? Remember, density is for a specific number, right? You don't need lower tail. When you need lower tail, it means that you want not just a number, but you want less than that as well, right? Or more than that number. So P, or which is like for calculate cumulative probability distributions, it's for like you want y less than or equal to something or greater than something. A range, not a specific number. A specific number always D. Same with the binomial, same with anything, right? If you want a specific probability of a specific number, always beginning with D. Okay, let's see. So this is what I'm using. The first argument, this is the value of y that you want. Right? So I want y equal to 0. Right? And the lambda, the second argument is the lambda, which is 1.5. You don't have to specify log equal to false. This is when you want a log version of Poisson distribution, and we don't want that. So the default log is equal to false. Or you can just ignore, you don't have to type this. and you can see that it gives me the same answers that I just showed you just now, and also like in the calculator that you see. It's 0.2231302. So if you only look at the final exam, basically, I'm gonna ask you two things, right? From last year, I'm gonna ask you to do this, to calculate using math like this, and then I ask you like, what are code you have to use? So you have to write me D Poisson 0, 1.5, and log equal to false is optional. You don't have to write. You can just close the parentheses, or you can like log equal to false. Anyway, it's the same thing. Okay, any question? Not that difficult, isn't it? I mean, if we do more example, okay, that is why, that is why I give you this textbook, right? We have the file of the textbook, this one, in the Google Classroom, because there are more example. If you want to work, right, you go to Poisson, and then it have, if we already use this, right? So it has some example, but it have exercises, and there are answers to this exercise in the back, right? For an odd number, right? So for example, any odd number question gonna have exercise in the back. You can like scroll down to here and answers to exercise, and it can give you 1.5, 1.9 question, that sort of thing. But the questions are more difficult, but you can have a chance to do exercise. So the more you do, the more you become confident in doing this thing. Okay. Okay. Let's go back to my PowerPoint, and let's see more questions. Example. Okay. Now we use the same thing, right? The same question that we have lambda equal to 1.5, and the length of textbook is 100 pages. But now we increase to 400 pages. Okay, so we increase the interval from 100 pages to 400. And the rule number 3 that I told you is that if you increase the interval or the number of space, the chance of the probability of success or the mean will increase in the same amount proportionately. So if we increase from 100 to 400, so that's 4 times. So everything will increase 4 times. So now we're asking what is probability that there are no typo. It's the same thing. We asked about what is probability of y equal to 0. Okay. And B, we ask what is the probability that there are 5 or fewer typos. So these are not specific number anymore. These are asking you what is the probability of y less than or equal to 5. Right? So if we're gonna use the code, this will use P Poisson, not D1. D1 is for this. But okay, so you have to remember that the probability of success is proportional to the size of the interval. So it used to be 1.5 per 100 pages. So if you have 400 pages, the lambda or the or mu or expectation of y will increase 4 times. So 1.5 times 4 is equal to 6. So even though they don't say anything about lambda, but it says that increase to 400 pages, so the lambda have to increase from 1.5 to 6. And that 6 is what you have to use to calculate. So you can see now that I'm using, instead of 1.5, I'm using 6, right? To the power of minus 6, 6 to the power of 0, and divided by, again, 0 factorial. But you can see that 6 to the power of 0 is still 1. 0 factorial is still 1. So this number it is e to the power of minus 6. And you can see that the probability is less than 1%. Okay, does it make sense? Okay, everybody? Let me ask you. So we have, right? We ask what, listen to what I'm saying. We ask, okay. Sorry. So we ask, what is the probability that you have no mistake? Okay, no mistake in 100 pages. And the calculation say 22%. Okay, in 100 pages, what is the probability of 0 mistake? It said 20%. Now, when we say like, okay, increase from 100 to 400 pages, what is the same? What is the probability of no mistake? Now it become from 20%, it reduced to, this is equivalent to 0.2%, 0.25%, so less than 1%. My question is, does it make sense? Is it? The guy in glasses? Yes, you. What do you think? We say that the probability of no mistake, in 100 pages is 20%, 22%. If it increases to 400 pages, the probability of no mistake is reduced to less than 1%. Does it make sense to you? If you have a book, right? If you have a book and the book is 100 pages, you think what is the probability that you will find mistake? Okay? And imagine that if the book increase in size, so from 100 pages to 400 pages, is there higher percentage of mistake or less percentage of mistake, of having mistake? Higher, right? Because you have 100 pages and you have 400. So 400, there are more pages, so it higher probability of making mistakes. So on the opposite, the probability of making no mistake have to be lower, right? Make sense? Yeah. So that's why I think this way of calculating mistakes in a book makes sense, because when you have more pages, they're likely that you're going to make more mistakes. And on the other hand, when you have higher probability of making mistakes, it means that lower probability of not making mistakes. So that's why it reduced from 20% to less than 1% when you increase the pages from 100 to 400. Okay? I know that when you see the math, you might think that it doesn't make it, it look difficult, but when you think about it, you can see there's reason behind why we have 20% in the beginning and now we have less than 1%. Okay? So you can see that I'm using the same code, D Poisson, and 0 is still my y. I want the probability of y equal to 0, but lambda has to be 6, and you can see that R will return the same number as here, but more decimal places. Okay, so the second question, for 400 page book, what is the probability that there are 5 or less typos? So this is like you have to calculate like the probability of y less than or equal to 5. So you have to calculate. If you use the formula, you have to calculate P of y equal to 0 plus P of y equal to 1, P of y equal to 2, 3, 4 to 5. So you have to use the same formula to calculate 0, 1, 2, 3, 4, 5. Do you know what people usually forget when they see this, right? Y less than or equal to 5, they start with 1. 1, 2, 3, 4, 5. They forget 0. You have to always remember that y start from 0, which means no accident, no mistake, no nothing. Same with binomial. Okay, so another way, right? Another way is we can use a table, right? I told you that you have to be able to use math table and the program. So if you again already you have PDF file of table of statistics in your Google Classroom, right? In table 3, you can see that it's a table for sorry, I have to pay it up. Okay, so the table 3 starting from this, you can see that it's a table for some probability, right? But you can see as well that this is like a binomial table. It cumulative, so it probably of y less than or equal to a. So if you want to find density, like the probability of y equal to just one number, like 1, you have to subtract two terms together. Okay, but what we want the probability of y less than or equal to 5. So we don't have to subtract anything. We can read off the table, but you have to find the lambda equal to 6. Okay, and you can see that the lambda starts from 0.02. So in the first half of the table, you don't see 6, and it go on to the second, right? And you can see that okay, the last number is 6 here. So that is lambda. But now you want 5, right? So you see that on the top, 5 is this column. Okay, so we go down and down and down and down, and then you can see that 5 and 6. The answer is 0.446. Okay, the probability of y less than or equal to 5 when lambda is 6 is 0.446 from the table. And this is the same, right? 0.446. So there is about 45% chance or 44.6% that there are 5 or less mistakes in your textbook when you have 400 pages. If you want to use R code, then you have to use P for songs. And it's number 5, lambda is 6, and you have to specify the lower tail to be true. Because we want to calculate the lower tail of the distribution, you want to calculate from y equal to 0, 1, 2, 3, 4, up until 5. And you can see that it's the same number as this, but we have more decimal points here. But if you round it up, you're going to have the same number. So the table, the math, and R have to be the same number, same answers. But you can see for our program, the advantage is if you look back to the table, if you look back to the table, right, you don't have, for example, if you have lambda equals to 5.7, you don't have in this table. But in R, you can key in any number and it can calculate it for you. So easier to use program to calculate the probability. Okay. Okay, Excel, you can do the same thing as well. You can get the same answers, but Excel is not what we try to test you. Now, okay, so we have, I think we have about 2 exercises. I will do one with you. Okay, so we have about half an hour. I can start continuous and not variable. Okay, let's do, I have more. Okay, which one is more difficult? Maybe Okay, let's try the easy one first. Okay, so maybe we might do 2 questions together. So the first one, this is from the textbook, example 3.19, right? Suppose a random system of police patrol is devised so that a patrol officer may visit a given beat location y equal to 0, 1, 2, 3. So you can see that this is already tell you that it has to be Poisson distribution because the possible value of y are discrete numbers, and also you have the time period of half an hour. Okay, and then it said with each location being visited on an average of once per time period. So this is your lambda. Lambda is 1. Okay, assume that y possesses approximately Poisson probability distribution. If I wanted to make it difficult, I'm gonna delete this information because when you see that it's half an hour period, when you see that y can be 0, 1, 2, 3, then you have to know that it's Poisson. Because we only studied 2 discrete random variable, binomial and Poisson, and when you have the time period or space, it has to be Poisson. It cannot be binomial. Okay, so you should know from the question that it has to be Poisson. So you have to make sure that you can, because some student, right? Let's say in the final exam you have 8 questions. So they work from 1, 2, 3, 4, 5, 8. But you don't have to work in that order. You can work in whatever question you think is easiest for you, right? And especially, it doesn't mean that question 1 is coming from lesson number 1 that I'm teaching you. So it could be from anything, right? So when we see a question, in order to know that it Poisson is binomial or in other distribution, you have to be able to read the question and then understand what distribution you have to use. That is very important. Okay. Because in real life, you have to be able to pick, right? You have a problem and you have to pick the appropriate distribution to use to solve your problem. So we want the question want to calculate the probability that the patrol officer will miss a given location. Will miss is mean y is 0. And what is the probability that it will be visited once, twice, or at least once? So you can see that it asks more than one question. It wants what is the probability of y equal to 0, what is the probability of y equal to 1, 2, and at least 1. So the 4 sub-questions. But it's easy because if you remember the formula, then you know the answers. Okay, so let's work it out together. So the question asks, so you have lambda equal to 1, right? And it have to be Poisson distribution. And the first question is, what is the probability of y equal to 0? So you have so you just so we have the formula is that lambda to the power y multiplied with e to the power minus lambda. Okay, I can switch the place. Y divided by y factorial. So lambda is 1, right? Y is 0, so you have that. Okay, so it's the same, similar to the question we did. You can see that eventually it boils down to just e to the power minus 1. Yeah. And if you press on your calculator, so that is 0.3868, sorry, 68. That's that first question. Next is, what is the probability of y equal to 1? So that, again, using this formula, lambda to the power y multiplied with e to the power minus lambda and y factorials. So now lambda is still 1, y is still 1. Okay, 1 factorial is still 1. 1 to the power 1 is still 1. So again, it's e to the power minus 1. So you can see that the probabilities remain the same. So the probability of y equal to 0 and y equal to 1 is the same. What about the probability of y equal to 2? So now you have lambda 1, y is 2, e to the power of minus 1, and then you have 2 factorials. Right? So 1 to the power 2 is still 1, so you have e to the power minus 1, but you divide it by 2 factorial is just 2. So basically it's just 0.3868 divided by 2, so it's 0.184. Okay, so nothing easy and nothing difficult. Sorry. So now the last one is the question asks, what is the probability of having visit more than 1? Read the questions again. Okay, last one. Okay, twice at least 1. So this is the question is at least once, right? So at least once, 1 is mean 1. At least 1 is mean that at very least 1 visit, but it could be 2, 3, 4, 5, 6. And it can go on forever because we know that we don't have an upper limit for y, right? In a Poisson distribution. So the probability that we have to calculate is the probability that y is greater than 1. Okay. Okay. So what is the probability of y greater than 1? So it is probability of y equal to 1 plus the probability of y equal to 2 plus, now obviously it has to be 3, right? And then plus 4, 5, 6, 7, but it go on forever because we don't know what is the maximum number of y. So how can we calculate this? Okay, how can we calculate this? This is like go back to the chapter about probability. Sometimes instead of calculating the real thing, we calculate the complement of it and subtract from 1. Okay, so we don't know y could be 4, 5, 6, 7, but we know that the only thing that is excluding from this is p of y equal to 0. Because we say like what is the property of y being at least 1? So it cannot be 0, it has to be 1 or more, right? So instead of calculating all the different probability, what we can do instead is just subtract y, p of y equal to 0 from 1. Why? Because whatever the summation of this, right? Well, if we sum this with p of y equal to 0, it has to be 1, right? But we know that this even is not including p of y equal to 0. So it's easier to subtract p of y equal to 0 from 1. And we already know that p of y equal to 0 is this number, 0.368. So it means that 1 minus this is 0.632. Okay, any question you want to ask? Okay, so now it will become more difficult more difficult than usual to use to calculate this. But let's see. Okay, for the first question, okay, let me get back to notebook. Okay, so that is the code for first question, right? We want what is the probability of y equal to 0 when lambda is 1. And you can see that I put 0 here to the first argument and 1 because of the lambda, right, to the second argument. And I still put log equal to false, and you get this. So this is the same, right? But we have more decimal point, but it's the same answer that we calculate using math. Now you can see that in the second command, I no longer specify log equal to false because we not want log. So and that is the default setting. So even when we don't type it in, it still set up log equal to false, so we don't have to use it. So we can just say the Poisson 1 and 1, so y equal to 1 when lambda is 1. So you can see that we get the same answer as before, and we see in our calculation already that p of y equal to 0, right, and 1 is the same, because it's equal to e to the power minus 1. Now, as for what is the property of y number 2, right? So we specify again y is equal to 2 and lambda is equal to 1 using the Poisson, and you get 0.1839397. So the same answers. Now it become slightly more complicated when you want for this. What is the property of y greater than 1? Okay, so so let's see. So we want something like greater than, okay? We want something greater than or equal to 1. Now, can you tell me the option lower dot tail. If you want that, if you want something greater than 1, lower dot tail have to be true or false. True or false? Okay, so if I were to draw a distribution, right? So I have start from 0, 1, 2, right? And that is y and then py. And for Poisson, right, the probability of y equals 0, we know that this bar will be, the height will be 0.368, right? And 1 will be the same, 0.368. 2 will down to 0. So that will be 0.184. So what I'm trying to do here is that I'm trying to draw probability density functions distribution of y when y is Poisson distribution, right? So, and like we can do like 3, 4, so it's gonna be keep like become less and less, but it's gonna be like this. So now we want 1, right? We want y is greater or equal to than 1. So it means that we want something like this, right? We want to start with 1. And then we want something equal to 1 or more than 1. So you can see that this is lower tail, right? That is upper tail, right? Because upper tails mean, because the number become increasing, 1, 2, 3, 4, 5, 6, 7, 8. Lower tail is something that is less than. So we start with 1, but we want the right hand side. We don't want the left hand side. So the lower tail have to be false. Okay? And that is the key. Now, I want lower tail to be false, and I want y greater than equal to 1. Okay? So, I know that according to my math, the answer will be 0.632. So let's go back to, okay? So you can see that I change from D to P because I want a cumulative. I specify lower tail to be false, right? We don't have to specify log.p, right? This is default, so we can delete it. And the second argument is the same, it's lambda, so it has to be 1. Now, I put 1 here, okay? So I say p points 1, y equal to 1, and 1, and lower tail to be false, and my answer is 0.264. Is that the same as what we calculate using math? No, it's not. Now, look at this second question, second command. I'm changing from 1 to 0. Lambda is still 1, lower tail is still false, and I get this 0.632106. Is that the same as the math? Yes? Okay. So you can see that you get the correct answers when y have to be 0, not 1. Can anyone tell me why? Why we want, okay, we want y greater than equal to 1, greater or equal to 1. But in the code, you have to put y equal to 0. Anyone can tell me? Okay, so this, I already talked about this a little bit in binomial, but at that time maybe you not fully appreciate what it is, but this, you start to see the problem, okay? So the problem is, well, the why it become more difficult because you have to realize this lower tail equal to false. Okay, let's go back to the graph I draw. Okay, so according to the graph, this is what we want. We want this, the probability of y equal to 1, 2, 3, 4, 5, and so on and so forth, right? However, you can see that in R, like lower dot tail can be true or can be false. Okay, and you have to realize that it calculates this when you specify when lower dot tail is true, right? It calculates y, the probability of y less than or equal to 1. This depends on the number that you want, okay? Now, when false, it calculates you the probability of y greater than the probability of y greater than 1, okay? So you can see that the probability of y equal to 1 included in the lower tail, not the upper tail. This is how R is set, because you can see that when you switch from true to false on lower tail to upper tail, right? We want the sum of this, right? This is y less than or equal to 1. This is y 1 and 1. We want the sum of this to be 1, because that include all possible outcome, right? One is y less than or equal to 1, so 0 and 1. Y is greater than 1, so it cannot be 1 now, it can 2, 3, 4, 5, 6, 7, and so on and so forth. So the R setting is such that when you specify lower tail and you supply number 1, the probability of that number is included in the lower tail, not in the upper tail. So now, what we want to calculate is, we want to calculate the probability. Okay, I put another color. Let me use the black color. We want to calculate the probability of y greater than or equal to 1. Okay? If we don't want, right? So when you have equal to 1, so that including, hiding here, is the probability of y equal to 1. If you don't want that, right? If you don't want equality, you may just like say y greater than 1, and I supply, I say like lower tail is equal to false. I can calculate that exactly. Okay, but when I want the probability of y equal to 1 to include it in my answers, I cannot just specify lower tail to be false, because it only includes y greater than 1, but not y equal to 1. Right? So that's why when we use the command, right? When we use the command, we get only 0.26, because this is not include the probability of y equal to 1. If we plus that with the probability of y equal to 1, you're gonna get these answers, the correct answers. But why? Why then when I put 0 here, you get the correct answers? Is because we put 0 there and we want, we specify the overtail to be false. So let me show you how R is calculated. Okay, so you can see that when you say lower tail to be false, right? And you specify y to be 0. So what are calculated is the property of y greater than 0. Is this the same as that? Okay? The property of y greater than 0, not including y equal to 0, right? And the property of y greater or equal to 1. Is these two guys the same? Is it the same? Is it the same? Okay. Okay. Let's say that y can go up to 5. Okay. So this including what? This including the property of y equal to 1 plus the property of y equal to 2 plus the probability of y equal to 3 plus the probability of y equal to 4, right? Plus the probability of y equal to 5. Let's assume that y go to 5, okay? Now, what about that? So that is probability of y greater than 0. So here, it includes the probability of y equal to 1, right? Yeah? Because it's greater than 0, it means it's not equal to 0. What about y equal to 2? Yes? What about y equal to 3? Yes? Yeah? Plus the probability of y equal to 4 plus the probability of y equal to 5. So you can see that it's actually the same thing. When you say that the probability of y greater than 1, greater or equal to 1, is the same thing as the probability of y greater than 0. Okay? So, what is this? This is like, you have to understand that is calculated in this way when you switch from true to false. So, when you use y to be 1, right? The probability of y equal to 1 have to be somewhere, and use the probability of y equal to 1 to be in the lower tail. Okay, so that is how R is set up. Now, what we want, right, is y greater than 1. So you have to figure out, this is what I want. This is how R is calculated. So, what do we have to put? Do we have to put 0 or 1? According to this, you have to realize that if I put 1 and lower tail to be false, it will calculate only y greater than 1, but not include y equal to 1. The only time that you can calculate y greater or equal to 1 is when you put 0 in the functions. Okay, so that's why, yeah, we have, when we use y equal to 0, then y equal to 1, lower tail to be false, you have your answers. Okay? Okay, so I don't have time to do don't have time to do the continuous, but I can do more questions. Okay, so let's see question number 2. Okay, example 3.20. Okay, listen. Okay, listen to this. So this is the first example that you see in terms of area, not the time. Okay, a certain type of tree has seedling randomly dispersed in a large area, with the mean density of seedling being approximately 5 per square yards. Okay, so you now know lambda is 5. Okay, now if a forester randomly locating 10 1 square yard sampling regions in the area, find the probability that none of the regions will contain the seedling. Okay. How can you calculate these questions? Okay, we know that lambda is 5, right? But it's 5 with the unit of per 1 square yard. But the question wants us to calculate that if we have 10 1 square yards sampling regions, and then find the probability that none of the 10 1 square yards have no seeding at all. So we have a tree, right? And the tree have seeds, and the seeds can be like floating in the air and drop onto the ground, and then you have another tree, right? So what they say is that if I'm marking 10 1 square yards, what is the probability that all of them have no seed from this tree at all? Okay, so now the question gives you lambda equal to 5, right? But it's 5 per 1 square yards. Now they want 10 1 square yards. What should we do? Should we multiply 10 to the lambda 5 and then calculate the probability of y equal to 0? Yes? Okay, so in the example of book, right, we have 100 pages, lambda is 1.5. Now we increase from 100 pages to 4. So when we calculate for 400 pages, we 4 multiply 1.5 lambda, right, to be 6, and then we calculate. But this is different because if we multiply with 10, right, it should be not square yard, right? It could be like a square yard. What square yards mean is that this. Okay. So you know a unit, right? Distance 1 yard, right? We don't usually use it. We only use it when you're playing golf, right? So a square yards mean that size 1 yard, and that is 1 yard. So the question want to trick you. They want to trick you in the sense that, so if we think, right, now lambda is 5 for 1 square yards. So now we have 10 1 square yards. So the question want to trick you to increase lambda to lambda equal to 5 times 10, and you have 50. But that is wrong. Why? Because that means that according to the Poisson distribution, the 1 square yard should increase to, okay, it should increase to 10 yards by 10 yards. If the area increased 10 times, then the lambda will be 50. But in this question, it's not that the area increasing from 1 by 1 to 10 by 10. It actually have 1 by 1, 1 by 1, 1 by 1. So basically what this guy do is he go around the forest and he randomly marking 1 square yards, 10 of this. So it's different from going from 1 by 1 to 10 by 10, right? This is just like the same size, but we have 10 different places. So let's focus on this first, okay? So suppose that if it's just 1 yard, okay, the way we calculate, because lambda equal to 5, and they want to know what is the probability that no seedling at all. So it have to be y, probability of y equal to 0. Sorry, I might go over time a little bit, but let me finish it quickly. Yeah. So if lambda is still 5, right, we use the formula. So we have lambda to the power of y e to the power minus lambda and y fact. So we have lambda is 5, y is 0, and e to the power minus 5, and then that is 0 fact. So this, right? So that is equal to e to the power minus 5, and that will equal to 0.0063738. Okay. Okay. So this is when we have only 1 by 1 yard area and lambda is equal to 5. The probability that you do not find any seedling in this area is less than 1%. Okay? But now, the question asking, what about 10 of this? Okay? So, the correct answer is not change lambda to be 50, but instead, you have to do this. The answer will be the probability of y equal to 0, and then you raise that to the power of 10. Okay? So it means the correct answer is that, raising to the power of 10. So, why? Because they're not enlarging the area, they have the same size area, but it have 10 of that. So, again, what we have here is, we have the joint probability of the 10 space have no seedling at all. When you have the joint probability and each one is independent, the joint probability is just the probability of y equal to 0 in all of the 10 and and multiply all of them together. So that's why we have the answer of y equal to 0 to the power of 10. Instead of changing lambda to be 50. And okay, so that is the answer. And let my last question is that, is this going to be smaller than that? When you raise something 0.0 something to the power of 10, the answer will be smaller than that or bigger than that? Smaller. So it means that when you have 10, right? When you have 10 space of 1 yard, the probability of no seedling at all is very, very small. Why? Imagine, right? If this is 1 square yard and I have 10 of that around my forest, right? If imagine I have 10 of that, and suppose that this is my seed, right? So I'm a tree, right? And then let's assume that if I throw this seed onto that piece of paper, right? It means that my seed for my tree, it actually drop in the area. So when you have 10 of that, is it higher probability of dropping the seed in this area? You have 10 targets instead of 1. Is it higher probability or lower probability of drop the seed in the 10? Higher, right? Because you have more target, right? So the probability of not drop seed on any one of them at all is very, very small. No. Right? So that's why, okay, it's tricky, but that's why here you can see that I'm using D Poisson, y equal to 0, then y equal to 5, I have this number, and then I raise to the 10 power. And you can see that in 1.9 multiplied with 10 to the power of minus 22. So 0.20, about 21 0, and then 19. So very, very small, because when you have 10 of this, it's unlikely that you're not going to drop any seed in them, in any one of them, right? Okay, I will see you again on